called Anity. So you see here the logo on the bottom left of the slide. So it's an artificial intelligence center in Toulouse, and it's 4 people you have in front of you. Valentin, Elisa, myself, and Philippe. So with Philippe, so Philippe is of course well known in nonlinear optimization and transformation method, and we have been working really for a while on multi-level optimization when you have nested models with various accuracy, and you want to get an efficient solver where you use each of those approximation of the function in a mathematically well-designed framework that is called the trust region. So we did this work in 2000. Elisa was one of our students, but now she's a permanent person at Ecole Normale Supérieure of Lyon. And Valentin Mercier is a PhD student from our institute from Anity, and his initial goal was to work on the shallow water equations and to make a prediction using machine learning. And it turns out that we managed to have 1 full year to work on whatever we liked. And we decided to invest our time and our joy and fun in the pins. So, and this is the work that will be presented today. It's what we call the multi-level pins, and I leave the floor to Philippe or to my colleagues to tell more about it.
Okay, Zogram, so you don't have to do the introduction.
Yeah, exactly. Thank you.
I didn't know it was just to wait. So now it's on green. You can do your job, right? Just
yeah.
The room.
You always all my job. Okay.
We don't need you anymore.
Yeah. Sure. I see there are almost 40 people online. So shall we start?
Yeah.
Yeah, I think Professor Serge Gratton has already done 98% of my job. So welcome to the current seminar. So yeah, let's start.
Okay, so thanks a lot. So today, as Serge was saying, we are going to present a little bit our work on the multi-level pins. So, okay, so as we know, we are working on the solution, the numerical approximation of the solution of PDEs, and Serge and Philippe has worked, and me too, for many years on classical approaches like approaches that require the discretization of the PDE and especially multi-grid methods. And we all know that nowadays there are a lot of advances in techniques from machine learning for the solution of PDEs, like physics-informed neural networks. So our idea was to try to transfer the advantages that we have in the case of multi-grid methods over classical solvers to the field of physics-informed neural networks. So that is from where our work started. So for today, we are going to do a brief recap on multi-grid methods. So I will start with this introduction, and then Valentin will take the floor and do a brief recap on pins. And then we are going to introduce our framework of multi-level pins. So starting from the multi-grid methods, so classically, when we want to solve a PDE, what we do is that we choose a grid, and then we discretize the problem on this grid, and we get a linear system that is often solved with a fixed point iterative method, such as Gauss-Seidel or Jacobi. And we know that it's really important to choose the size of the grid correctly, because this will have a deep impact on the accuracy that we can get on the solution approximation. But on the other side, we have to be careful, because if we want to have a good accuracy, we need a fine grid, but at the same time, using a fine grid will demand us to solve a really large scale system, which can be difficult and expensive. So multi-grid methods answer to this question because they try to make the solution of this system cheaper by exploiting the fact that the problem can be represented at different scales. So we are really exploiting the geometry underneath this problem. And so the fact that it can be represented at different scales. And so this is efficient from two different points of view, because on one side, we know that if we reduce the dimension of the problem, we can solve it with a lower computational cost, but also we can really take advantage on the fact that each scale of the problem will allow us to efficiently reduce different frequency components of the error. So this is something that is well known. So the fact that the behavior of methods such as Gauss-Seidel or Jacobi are deeply dependent on the wavelength of the solution. So this can already be seen on a really simple problem. So for example, the Poisson problem. If we take as an initial guess for our method different Fourier modes corresponding to different frequencies, k, so we can see that if k is low, so for example, k equal to 1, this corresponds to a wave that is really smooth. On the contrary, if we take a large value for k, we can see that this corresponds to a wave that is highly oscillatory. And it's really interesting to run this kind of fixed point method starting from this initial guess, because we can see a really different behavior depending on this value of k. So we can see that when k is large, these methods are quite effective in reducing the error, while they have great difficulty when k is small. So this is a property of fixed point iterative methods that is called the smoothing property, because we can really see that the methods are really fast in reducing the highly oscillatory components of the error, and we obtain so really quickly a smooth wave that is really hard to approximate. So multi-grid methods really take advantage of this fact, and the idea really is simple, because the idea is that we can exploit the fact that we can represent the problem at different scales to attack different components of the error depending on different frequencies. Indeed, the idea is that if we consider a wave on a fine grid and it appears smooth, we can project it on a coarser grid, and we can notice that it will appear as much more oscillatory. So we can imagine that the same method that has difficulty to attack this wave on the fine level will be much more efficient on a coarse level. So this is really the basic idea of multi-grid methods. So for example, in the two-level case, we will consider, instead of simply a fine grid on which we can obtain a good accuracy on the solution, we will consider two grids, a fine one and a coarse one. And so we will consider two different discretizations of our possibly nonlinear system that represents the PDE. And we will try to target different frequencies of the error by writing the solution as the sum of a fine and the coarse term. So the basic elements of multi-grid methods are transfer operators that allows us to move from one grid to another, and so to transfer the waves to from finer grids to coarser grid and vice versa. And this is really important because once we have written our solution as the sum of these two terms, we can attack them in an alternate fashion. So the idea is that we start on fine level, we apply a smoother that will eliminate efficiently the highly oscillatory components of the error. And then we consider what is called the residual equation, but we solve it at coarse level. So this will allow us to reduce efficiently the smoother components of the error. And so then we get a correction, a course correction that is then projected back on the fine level and used to improve the fine level approximation. Of course, this is the simple scheme in the two-level case, but it can be easily extended to the case in which we have more than just two levels. And the typical scheme that we use is called the V-cycle, because the idea is that we start on the fine grid, and then we go down until the coarsest level is reached. And then we go back up and we repeat this V-cycle in a cyclic fashion. The great advantage of multi-grid methods is really evident in practice, but it can also be proved in theory that we can reach the optimal complexity for some problems. So of course, multi-grid methods are not useful for all the problems, but they are really effective for problems for which it is possible to separate the different frequency contributions. So the case in which we have in the Fourier space a diagonally dominant matrix. So in this case, the frequency components are well separated. There is a really weak coupling between them, and so we can reduce them efficiently by attacking them in an alternate fashion. Okay, so now I leave the floor to Valentin for the introduction of the pins.
Elisa, can I ask you a question?
Sure.
Your group works also on non-elliptic problems, where like even for elliptic problems, for example, with the very large aspect ratio, all these anomalies that multigrid is not optimal. Is your group trying to advance those type of like non-elliptic problems, large aspect ratio?
For the moment, we have started from the elliptic case, so we are really in the beginning of the study, but then we will, of course, this is a perspective of our work to address more complex problems.
Yes, yeah, so we have, Elisa, we have also another work that we've done with you, where we don't work necessarily on grid, and we try to use ideas from algebraic multigrid,
right?
Yeah.
And define and find the transfer operators by analyzing directly the spectrum of the matrix. Today we are not going to present work in this direction, but we also considered a less structured problem, but not with pins. So we it was a different approach where we try to precondition in fact the solver.
Okay.
Yeah,
okay.
that is interesting. It works well. It's an approach that works well. The only problem is that we need to have access to the Hessian matrix. So it's good for problems that are not really too large.
Yes, thank you. You can proceed.
Okay, so I take the floor. So I will not present you a lot the PN because obviously you know it. We'll just say that it's a solver that imposes in a weak way the respect of the partial differential equation and the boundary condition or initial condition and some measure if we have some, but it's a solver that integrates the physics knowledge in the loss and first in the optimization problem, but you know that. But that will be the solver that we will use next to make our multi-level method. So one thing that characterizes the PIN and characterizes all the neural network is the spectral bias of neural network. What is the spectral bias of neural network? It's a theorem, especially the frequency theorem, that states that the neural network is good to handle the low frequency component of the data that he use and of the function that you want to approximate. That's why the neural network are used extensively in with picture, because in picture, the high frequency are often the noise, so you want to avoid them. So it's a classic denoiser, but it has some difficulty with to handle the high frequency component of the data and of the function. So that's a perspective that not enjoy us, because it's the opposite that what we want from the multi-grid method that handle good the high frequency and harder the low frequency. So we want to develop some methods to make them attack in a better way the high frequency. So this has been proved in PIN by Paris, Perdicaris, and all this team that was stated in this paper. They use the neural tangent kernel method that state that we have some infinite wide neural network and an infinitesimal gradient descent to make an approximation in a system of equation with some matrix. And they show that there are some favorite way to optimize the gradient that lead to low frequency component. So it showed that it work on the PIN, and it also show that there is a dominance relation between every member of the loss. So there is a dominance relation between boundary condition and between the PD respect, and also the initial condition or Mercier if we have some respect. So it's a very interesting paper, and we going to use that to understand some method to target frequency, high frequency, low frequency, middle frequency. So after this paper, the same team released this paper that transfer the use of Fourier mapping in the PIN framework. So they use Fourier features, that is a Fourier mapping described here with a matrix that is sampled from a Gaussian distribution, and that allow the network to handle in a better way the high frequency data and attack in a better way the high frequency data. So they show this with several equations, and it's allow them to attack this equation with a multi-scale component in a good way. But there is some problem with that, not problem, but some more hyperparameter, because we have to choose the distribution of the Gaussian, and it affects a lot the frequency that the network can handle, but it's a first step to handle the frequency. There is also the work of Weikai and his team that first propose a network where we shift the input data from high frequency to low frequency. So we segment the Fourier space in several frequency segments, and we shift the segment to low frequency one, and a lot of little NN could handle this data that were shifted to low frequency, load them fast, and then with another shift, we shift this frequency to high frequency and we reconstruct the signal. So it's a good way to start, but there are some problems because the shift required a lot of computational cost, especially when we were handling high dimensional data. So it was not reasonable to use it, and it's not good because the advantage of the neural network and PIN especially are that they can handle high dimensional data. With a little dimensional course. So they try to propose this formulation that you see there with Fourier decomposition of the network. So AM and BM are neural network, and they use a lot of subnetwork that attack different frequency represented by WM that you see here. But it have the same drawback than the first paper that I presented before, because you have to choose the frequency that you attack, and it's an hyperparameter. But then they propose another way to see that in the multi-scale networks. So the first idea is to do another decomposition of the Fourier space, but instead of doing a classic decomposition in all the dimensions that you add, you do a decomposition, a radial decomposition. So you have only one direction where you can shift the data. But again, the convolution that they want to use here are too expensive. That's why they propose to take an idea from the wavelet world and to use a new activation function that were activation function compact in the space that have compact support in the space. And there's compact support function that you see here. So H value, it's a product of two value function, have particular behavior in the frequency domain. So you have here the Fourier transform. You see that when you scale the entry of this function, the Fourier spectrum take a wider range of frequency. So they use it to construct multi-scale DNN that you have on your right. So you scale the NN, you scale the entry with different scale value, and you learn to the subnetwork to target different frequency range. But it's a simultaneous training. So you construct the network and then you train it in a simultaneous way. Everything is trained in the same at the same time. It worked very well. You can see here that it handled some Poisson, I guess Poisson-Boltzmann equation in 2D domain with some special boundary condition inside. And you are here the classical pin with desactivation function. So with a S-value activation function that handle it a little weakly. So we have a lot of tools to target different frequency, and with that we can use it to transfer the knowledge that we have for multi-grid method to the NN world. So that's what we made. That's what we made with multi-level pins. So what is a multi-level pins? It's like in the multi-grid world, a sum of several pins. Here you have an example with 2 pins. You see that we define our output like it was done in multiscale, like a sum of subpins, and we apply the PDA system on it. And we have several optimization problem with one for each subpins. So there is an indicator here on the first pin because it's the pin that we will train in this problem, and on the right problem you see that it's with the caps H U pin. We train only this pin. So you see also that we train on different sampling. That's because there is a paper that states that we can target more easily high frequency with a finer grid. So that's what we make with here. That's what we try to make here with several sampling, and also because it have a different cost to optimize on a bigger, on a lower database. So to be more clear, here we have a drawing. So we exploit, like Weikai did in his work, the scaling entry and the compact supports activation function to make our subpin target different frequency. But we train the spin in an alternate way. That's what makes the difference. So we propose a framework to train them in alternate way. So you see we have some hyperparameter here. So V1 and V2 that are the epoch made on our optimization problem. So here we perform V1 epoch for the fine minimization problem that target the high frequency. So here in red and with this grid. And then when we finish, we transfer the data that we need to compute the other optimization problem. So the derivative of our subnetwork is value on the grid inside point and on the grid boundary point. And then we train our network that targets low frequency. and we do it in a cycle way. So here you have what we call a V-cycle, because when you unfold it, it looks like that. But we have a V-cycle with only 2 stages. You can make it with 3 stages, 4 stages. So what is the interest? First, we have a prior that states that there's a network targets different frequency range. So we don't want them to interact between themselves, because they will attack in some way the same frequency region, and it will not be good for the training, but we will see that later. And then we train an initial training on the first, because we have to start somewhere. So we train our first network. Then we extract the required values, like I said. So in the Poisson problem, it would be the second derivative for each space component. We do it one time between 2 training, because we don't want to have the derivative cost in terms of computational cost make at each epoch of each subtraining. So we make it once. We transfer the data to the low frequency training. We train it, and we do it in a cycle way. So that
can I ask a question? So you have 2 grids, right? You don't have random grids. You have regular grids.
We have regular grids, yes.
So you bring back the grids. So the grid itself is the one that defines the just like in multi-grid, right?
Yes, it defined. We choose regular grid because we want it to be interpretable, and it's a first step. But we obviously can do it with hyperlatin sampling, like in the other PIN paper. But it's not the it's the thing that allows us to target more easily high frequency when you have more sample. But the scaling in entry and the S-ReLU activation function also do the job to target the frequency that we want.
And here you don't use any smoothers. The neural networks are regularizing the solution, right?
Yes.
And there's no like, okay, yeah.
We don't use any Jacobi iteration
right.
between. Or...
Yeah.
So
are you going to show us the new 1 and new 2? How many iterations you take? You have those results in the algorithm?
Yes.
Yeah. Okay.
Yes. Because they don't have to be too small. Because if we are too small, the overhead of the GPU cost is too strong, and we want it to be efficient in a computational way. It have this cycle implementation have some advantage, because even if it's not parallelizable, because you train it in a sequential way, you can put this network on different GPU. We didn't have the time to do that, but it's a way that it can be optimized, because some GPU doesn't have the memory to handle the derivative operation, the derivative graph. So if you want to optimize this, you have to implement it on several GPU, but that's not the point. But it's an advantage of this way to see the thing. So there is here a simple Poisson problem in 2D that we want to solve to see if our method works well and works better than the previous method presented, like multi-scale. So we take a Poisson problem on a square, classic, with a null boundary condition, and we take the f function to be first the solution of our problem is this expression. So it's a classical solution in multi-grid problem, because it's a way to show a different frequency in the solution. So here you have for different value of beta different solutions. So you see that it's as beta increase, the frequency of the solution increase. And because we solve the problem in the PIN way, we have to look at the second member, that is f, and we see that the frequency is much higher in f because it's a derivative, and there is some value that go out when you derive this expression. So that's our problem. How does our network behave on this? I will first show you the experimental settings. So for the pins, classical pins with hyperbolic tangent activation function, we have 2 hidden layers with 300 neurons each. For the M-scales network, we have 4-sum network, like presented before, with 2 hidden layers of 150 neurons each. Input scaling used are 1, 2, 4, and 8. So it's what they made in the paper. So it's a classical way to use this network. For our 2-level MPINNs, we have 2 subnetworks of 2 hidden layers and 210 neurons. We train this in a bicycle with 1 and 8 input scaling. So you ask about the parameters, they are here. We make initial training with 1000 iteration. Then we make 4 bicycle with 1000 epoch on each subproblem. We have a 3-level MPINN, so the bicycle that I showed you earlier, but with 1 stage more. So we have a 3-sum network of 2 hidden layers of 150 neurons, and then it's trained the same way. There is 1000 epoch for each subproblem. Why do we choose this value? It's because in terms of forward computational cost, it's the same for all the network for the epoch that we'll show you. So it means that if they are correctly implemented, so with no artifact of the framework we use, so if they are implemented in CUDA directly in the GPU, you have the same forward cost that is the strongest cost in the training for all the network we present. So you can compare it based on the loss value and on the mean square of YAL value, because the computational cost is the same. So we take a regular grid sample of 80 times 80 points. And in all the cases I will present you, we make 10 run with random seeds, but the same seeds for each model. And then we make a median of it to have some generalization property.
Hi, can I ask you a question on that slide? This is Michael from Utah.
Yes.
Have you studied different sampling techniques for the regular pins? I understand that here, like George said, you reintroduce grids for the MPINN, which makes sense. But in my own experience, pins don't require grids, and using grids over sampling methods like Latin hypercube actually makes it train worse to an order of magnitude. So it seems like you're in. Have you studied that at all?
I used Ecole before with the same method, but I used grid here just to get the same idea that we have in the multigrid. But of course, we have to try different sampling method. I didn't know that there was some order of magnitude difference between the two training. I just took the value that we have in one of the proof of pins conventions that state that we have to have a square difference between the inside value and the boundary value. That's all I was based on.
Okay, yeah. Yeah, I mean, as George said, you're reintroducing the grids to pins, which is a part of the.
Yes, it's a mesh.
The benefit is they're meshless, right? And,
yeah,
and they learn better on meshless sampling as well, on like random sampling, not grids.
Okay, but I made it with Ecole sampling. I did not witness any differences, but I guess it's depending on the equation also and on the solution that we are aiming for. So I will take note of that, and for further experimentation, I will do the both.
Okay, cool, thanks.
I have seen Mike's results. So random sampling, he has shown that random sampling. I think the theory, at least for DeepOPerator, show that. Oh. Random sampling is almost optimal.
Okay, so I trust him. I didn't know. That's all. Yeah, I have no doubt. So that's our experimental setting. The value that I will show you are expressed in this way. So you see you have the epoch on the x-axis, and here the loss value on the y-axis. You saw that I write here hidden iteration. What is hidden iteration? It's because we make this training in the vesicle way. So obviously we have more epoch in the vesicle ways because we train sequentially each network. So when you have this discontinuity here, this drop, it's because there is the subpin that are trained, and the loss that I plot is the loss that we measure on the high frequency pin. But
Valentin, can I ask a question? So you didn't normalize, right? Because I see some huge numbers here, 10 to the 6. You didn't normalize your input output.
Yes, I normalize.
But why do you have 10 to the 6 as a value?
I normalize input, but it's because the derivative, the second derivative of the output, make output the frequential coefficient inside the sinus.
Yeah. So you normalize the inputs only.
Yes.
Okay.
So as you can see, there is some identification here. There may have some rebound that we can see under my mouse here. It's because at each transfer of information, we have to restart the Adam solver, because the momentum that was calculated for the problem is not longer available, because you change the problem each time you compute the derivative and you pass information. So that's why there is some rebound here that are not optimal, but that seems to work with that. So we choose to restart Adam at each exchange.
Hi, Valentin. Can I ask a question?
Yes.
Hi, my name is Andrew. I'm from Crunch Group, current PhD student. Sorry, could you go back to the previous slide? Sorry. So I'm wondering how many iterations are there in the hidden part, since I know you want to do a comparison. So I think probably it would be helpful to expand that and plot them with the same horizontal axis. So
it's because here I gave you the hyperparameter. So you see here, I say that I made 1,000 epoch. So here, when you have the 2-level MPIN, so in green, dark green, the jump that we have here is the 1,000 epoch made on the low frequency subnetwork. Here, because it's a free level, you have 1,000 epoch made on the middle network, 1,000 made on the low frequency one, 1,000 made on the middle, and then you go back. So there is 300 hidden here. But that's why I say that I take a subnetwork of lower sizes, because we want to keep the computational cost constant. So when you are here on the jump at 1,000, 2,000, 3,000, you have exactly the same computational cost for each method.
Okay.
Is that clear?
Yeah, I see. Yeah, thank you very much.
Okay. So we made this experience by varying the frequency content, like it was made in multigrid. So we can see that multi-scale method often fail to do better than pins, except with beta is equal to 9. You witness here the global loss of each network. And there are two methods that show that they are available. There is PIN. So PIN with beta equal 3 are in the comfort zone, because it's low frequency component, and they are doing a great job. There is no reason to change them. We see that our method with the frequency, with the multi-level training, achieve approximately the same loss value. With beta equal 6, we have approximately the same comportment that with beta equal 3. But when we take beta 9, the pin start to fail to train. The multi-scale method first go very quick to what seems to be a step. And our multi-level method train very well based on the loss value, and especially when it's a free-level method. And with beta is equal to 12, we see that PIN have somehow a regain of confidence and try to do better than multi-scale, but they are not comparable to our method with free level 2. So that's for the global loss. We can also see that monitoring the boundary loss, the multi-scale activation function allow the network to keep low the boundary loss. So it's allow us to be closer to the system solution, because the PDU solution is conditioned by the boundary loss value, and that's what we see on the next slide here. We monitor the mean square error of our problem. So we see that our methods are always better. It's because even when the PIN method or the multiscale method have a good loss, they don't have a good boundary loss value, and it's make them far from the real solution of our problem. We have some. We are trying to do some work on how this alternate training allow these networks to keep a good boundary condition value, because it's a phenomenon that we saw from the start that we try to work on this method, and we start to have some direction of work using the neural tangent kernel analysis, because when you use that and you make a multi-level training, you see that the eigen direction that push the training on the way are somehow combined, and maybe, and I say maybe because we don't have any proof yet, the dominance between each loss is regularized in this way, because we have a lot of some network, but it's this work is at the start, so I cannot say more on that because we don't have any proof.
Excuse me, this is Lulu from Japan. So I have one question for this slide here. So how do you define the MSE? This is the MSE between your prediction of the network versus
yes.
the ground truth.
It's the MSE between the true value and our network output, and it's made on the. That's why I wrote extrapolation. It's made between a very fine grid, finer than the training one, to have an extrapolation ID of our network.
Okay, but it's still interpolation, right? But anyway, so but I look if like the MSE. So if the MSE, for example, in the first figure is 10 to -2, if we do the square root, which is the absolute error, then would be 10%, right? Do we have the relative something like relative L2 error?
Yeah.
Or?
No, I don't have relative MSE on this one yet.
Right. Because MSE is a squared error. If we divide square root, then
yes,
the error would be large.
Yes. It depends on the function value.
Okay.
It depends on the function value. I've made some experiment with two at the start when we used classical pin, not MSK, not S-ReLU value in this way of training, and we have an error on the same problem approximately on the order of 5%. So if I can give you a clue, with higher loss value, but I don't have it on the slide.
Okay, thank you.
Can I also ask a question? Have you compared with CPIN? You know what CPIN is? So in other words,
conservative.
So instead of one domain, you can have two domains. When beta equals, let's say, 9 or something, or 12, you can have 3 domains.
Okay.
Divided domains, and then that's a more fair comparison, because you have 3 pins, and each pin basically sees, since it worked for 3, right? So 3 or 4 pins work well. So each pin will work on that many frequencies. So
yes,
that's a more equivalent comparison.
It's equivalent to the M scale too, because we have the same number of subnetwork. But I see what you mean. Conservative pin, the pin are working on different I'll say that. Like a domain decomposition way, or on the same domain?
Yeah, because these frequencies are in space, right?
Yes.
So
no, there are frequencies.
Yeah, these are waves. Yeah, you show us beta equals 12. You could see that you show us the structure. So it's if you divide that by,
yes,
if
if we zoom on it, there is a lower frequency. That's what you want to say.
Right, exactly. Okay. Yeah. Same idea, but different implementation.
I'm not sure about that because I'm also work on domain decomposition pin.
Yeah.
And there is a very high frequency component here. So if I take 3 pin like it's made on the 3-level MPIN that you see here, I'm not sure that we can divide the domain in a way that the frequency will be reduced because the frequency are in the both axes. I don't know if you.
Yeah.
So I'm not sure we can zoom enough.
Right. Okay. Of course, you can use adaptive activation functions, but Maya is not here, so I'm not speaking for him. But anyway, you keep going.
Okay. So I just said we for the experiment that we saw before, we have the same grid size between the 2 pin and all the 3 pin in the 3-level MPIN. But we can vary the coarse grade size. It's one of the interests of the method because it's lower the computational cost. So what you see here is the computational cost of the forward pass in flop on the x-axis and the loss value on the y-axis. And you see we vary the grid size. So from 80 × 80 to 40 × 40, and we see that we end before because we have obviously lower computational costs, and we see that if we want to reach lower value of the loss function with less cost, we can do this, but by lowering the grid size. So it's an hyperparameter that we can use to manage the cost of our method. So it's an interesting way to get it fit to our GPU or our CPU that we use. And it also shows us that we don't need to have a very simple to target low frequency, as it's stated in the article I talked about earlier. So that's I know that it's an experiment on one type of problem, and we are making experiment actually on other type of problem, but it's a work that is at the start, and we have a lot of perspective. But first, let us conclude. What we present to you is not especially a new type of pin because it's used previous work, but it's in another way a framework that use the idea of the multi-grid training to train a pin type problem, but it can use with a lot of other method and a lot of other network. We talk about adaptive activation function. I talked earlier about Fourier features. It can be used to do the same thing, and it will be used on the near future to do the same thing and to compare if it works well. So we have to see it like a framework. And we have demonstrated that exploiting the spectral complementarity of all the sum network, we may bring some computational gain, varying the sample in input. So we have to try Latin sample, but in the same way, we can vary the number of points that we take. And as perspective, we have, as I say, have to do extensive testing. So on other problem, but obviously with other pin type, other DeepOperator type, because we can use it to train DeepOperator 2 with Fourier features mapping and with Latin sampling. We also have to pursue the sensitivity analysis to have some range for the hyperparameters, and we investigate theoretical aspects, as I say to you, about dominance of the loss and the convergence of the whole method in an optimization point of view. So thank you all for listening to us. And if you have some more questions, we are here to answer to them.
Hi, hello. This is Adar from Brown. I have a small question. So I was wondering, like in multi-grid methods, usually you do a smoother and then you go a step in. So the smoother usually takes care of the high modes, and then you go a step in for the lower modes. I was wondering, like, I guess that here you expect the first, like the highest level of your MPIN to take care of like the higher modes, but it's also kind of limited because it's a pin, right? So can you say something about that? How, like, what do you expect to get at the end from, compared to a multi-grid?
It's based on the work of Ecole that I showed you earlier, because as you see, the activation function, as I said before, take a different range of the frequency value. So we expect to eliminate the frequency of the lower frequency of the residual problem using our low frequency network. So it will eliminate the frequency that the higher frequency network is not made for solving, and using this cycle and the residual between each problem, we expect them to take care of different frequency range.
I see. Yeah, but it's still limited. I mean, like,
yes,
it's not like the multi-grid that is like expects to reach machine precision or something like that. It fixes some, right? Because we are in multi-grid, we usually expect it to completely eliminate the errors. But here you don't, right? You're trying to improve the error, but you will never be able to
fully
handle the high modes,
yes.
right?
So maybe if I can add something, on multi-grid, you are trying to, maybe the limit you can reach is the discretization error, right? So, and here you are also, you cannot go further than what you can get with the sampling you perform. So there is also in multi-grid, you can solve the linear systems to full precision, but what you would compare in this work, we compare with the true solution at points that are not part of the sampling. So, and this contains also the discretization error. So you may want to put here, even for the multi-grid, you would not go to machine precision. You would have the something related to machine, to the discretization error, like H square or something like this.
I see. Okay, thank you. Thank you.
Hey, Valentin, this is Raj. I have a question. Can I ask a couple of questions from your presentation?
Yes, of course.
Yeah. So can you provide some insight of implementing this method for hyperbolic problem? Because in that case, you have a sampling in both time and space. So how would it behave actually? Because here you have shown only for wave numbers, like how to sample the higher wave number accurately.
Excuse me, I didn't understand.
So
can you repeat, please?
Yeah, how this method will behave for the hyperbolic problem, like wave equation.
So Valentin, when you have time,
okay.
not only space variable, the space and time.
Time, yeah.
Okay.
So you have a evolution in both space and time. So
I'm actually making run. I make this afternoon, but we are trying to handle this same problem with initial value, like the wave problem used in the article that I cited a bit earlier. And we are trying to use this method here, and we don't have the results yet, so we cannot state on how they will behave.
Okay.
But maybe you can say about the methodology, Valentin. So how you would use sampler in space and in time. I think this was the question.
Okay, I think the sampling have to be done the same way that we did before, because there is low frequency. You can see the time dimension as a spatial dimension, and the frequency that you have in time have to be treated the same way, because it's also an input feature frequency. So I guess at first I will treat it like the other dimension, but I know there is some work like with the Fourier features network, where they use a specific part of the network to handle the time frequency with another Fourier feature mapping. So maybe we can think about using subnetwork, another entry especially dedicated to handle the frequency in time domain.
Okay. So on this slide 33, the flop is a GPU flop or CPU flop?
The flop is forward pass flop.
No,
so
no. Is it for GPU or the?
It's not measured. It's calculated because we talked with a friend that work at NVIDIA, who tell us that the most of our measure that we will have using framework like TensorFlow 2 or PyTorch will be from framework artifact, and he tells us that we should calculate ourselves the computational cost and not measure it on GPU because it could have some noise on it, and so it's a mathematical formula that we use to this. So we use only the forward cost that is marginally dominated by the matrix product between the two hidden layers.
Okay, I don't know. I got that, but I think in GPU you can compute the flops, how much flop it is crunching. So
yes, I can, but
I just wanted to say that, like, whether it is a real representation of cost or just a complexity.
No, it's a time complexity. If it was a question.
Okay, thank you.
May I ask another question, please? Can you go back to the slide of the V cycle?
Yes.
So what is the interface between the course and the, like, I understand that you kind of like shut down the first level and then you train, like, first of all, you train the first level, the fine, and then you shut down the fine and train the course. I got it correct?
Okay. Yes.
So what is, like, is there an interface between those? Like, are you using information from the cursor step?
What we do is that we infer our fine step of fine network on the course grid. So we have an output. We use the classical automatic differentiation tool to extract the value that we need to compute the residual of our problem. So we extract, like I wrote here, the second derivative, for example, the value on the inside points of the course grid, the value on the boundary point, and then we have just tensor or value, with the size correspond to the course grid, and then we give this tensor value to the low frequency training because we make the residual problem optimization problem. So we subtract what belong to the PDE to the second member, and we do the same on the boundary. So the interface is just an exchange of tensor.
I see. So essentially you have the fine grid and the coarse grid, and I can imagine that, like, you have a forward that goes through the fine grid, fills the points on the grid, and then you pull only those points on the coarse grid, then you put them to the coarse grid when you do the inner step. Have you experimented, like, instead of like I don't know, putting those inside, because okay, the coarse grid also computes the values, right? So
yes.
Maybe taking some averaging between them, some, I don't know, maybe
like a transfer operator,
something
maybe?
like that. Yeah, like, but how to choose the, like, you have a point which resides on both fine and coarse grid. What value this point is going to get? So I understand you can just put the one from the fine grid because, yeah, that makes sense. But maybe the one that was computed for the coarse grid for this specific role, and this can be more accurate. So maybe either
as the output of the network is always defined as a sum. So it's always the two values are taken into account, but there is only one value that is training. And we use the property that PIN are interpolator and act a continuous way within the within the input space. So we use them as a reduction and interpolation method, and interpolation and extrapolation method. So they are used as the operator of the multi-grid method. I don't know if I am clear.
No, it's clear. Yeah, I understand. That's great. I was just suggesting to maybe take like some combination of those values from the fine and the coarse, maybe weighted combinations, and the weights could be also trainable to see which one of the grids contributes for more accuracy. I don't know, something like that.
Oh, okay. So maybe one more network that only train on the transfer value somehow.
For example, yeah, and just explore what happens if you do that, or something like maybe a combination would be a better, like not only the transfer need, or only some combination between them may benefit.
So if we take back to the optimization problem, you suggest to add some trainable weight on the useful definition.
Maybe, yeah.
Okay.
Yeah. Because like the UH might be for some problems more correct than sorry, the UH. U capital H might be more suitable for some cases, and U lower H depending on the smoothness and things like that. So
okay, yeah. That's a great idea.
Cool. And great work, by the way. That's very interesting. Yeah. Thank you.
That's an idea to try.
Do we have any more question for our speakers?
Maybe I have a question for the audience. I'm sorry. So in fact, we have this method that seems to be quite robust and works reasonably well on academic examples. And of course, we would like to analyze mathematically what's going on there. And what I think the current theories that we have in mind are probably based on the tangential approximation of neural networks. That's what Valentin mentioned. So basically, you interpret the gradient descent as a continuous process. And then you look at the ODE that the loss is a solution of, and you try to interpret in terms of eigenvalues of the matrix involved in the linearization, and depending on the eigenvalue of this matrix, you understand whether your error is converging fast or not. What are the tools that you use in general now for studying the behavior of pins? Do you have other recent tools? When the problem is nonlinear, and since pins are nonlinear, we guess that there should be some linearization to get speed of convergence on practical problems. So what is the state of the art for that, you think? I don't know for who the question is. I don't know if you have any paper to mention to us.
Okay, thank you, Serge. I like to remind you that George was going to another meeting. He's currently at Caltech. He's not at Brown. So is anyone from the audience that can answer Serge's question for PIN? How about this? We can talk after the seminar. How about that?
Okay.
Like you guys and us with George. I'll email him for.
Okay. Excellent.
Okay. Great. Thank you. And thank you, Valentin, for the wonderful presentation. And we have a lot of questions because we're really interested in it, not because we love it.
And I have a lot of way to improve what I've done. I note some of them to more comparison and Hippolytan sampling, obviously, and some way to progress. So thank you very much. It was very
no problem.
Interesting for me.
Yeah. Okay, so now we move to our second talk. Our second speaker is Mathieu, who is currently a PhD student in computer science. He's supervised by Thomas Schacht from Brown University and Rufen Van from the Artificial and Natural Intelligence Toulouse Institute. And Mathieu's current research interest is about how artificial and biological intelligence learn and develop, and how this optimization and dynamic system theory can help describe the learning and development process. So without further ado, let's move to our second talk. So Mathieu, are you there?
Yes, hi Duncan. Thanks for the introduction and hello to everyone.
Yeah, you want to take over. I think you're able to share your screen.
Okay, let me try. Can you see my presentation?
Yeah.
Cool. Okay, so let's start then. Thanks for giving me the opportunity to talk today at this seminar. I'm going to present a model that I've recently developed in collaboration with Bora and Hadar in George's lab. As a disclaimer, I would say those are preliminary results. So from the empirical side and experimental side, it's still lacking some of the results that we would like to show with this new model. The interesting proposal and why I think it could be interesting for you is that it uses some of the tools that have been developed in George's lab, such as the DeepOperator Network. And the idea of what I call ENCODE for normally controlled ordinary differential equation is to learn operators that are influenced by control signal in a new way that is hybrid in the sense that it uses deep learning as its core to define a vector field, and it uses tools from classical numerical integration theory, such as classical integral solvers. So yeah, to give you a bit of context, we are in an era of data-based approach for modeling physical systems, as I was saying, with a need for either system identification, where we have no a priori information on the model that we are trying to fit, or on the other hand, when we have this a priori information, to inject this information in the training, such as with the PIN that the previous talk was talking about. And of course, this deep learning is very powerful tool to achieve this goal, but it has some loophole, especially the weak generalization property that it has. When we fit a model, there is no generalization outside of the training domain, and which is opposed to the classical literature for instance, integrating partial differential equation, which have property that which let the solution being evaluated to a longer time domain than what we have seen with a database approach. Personally, I'm more of a computational neuroscientist than truly working with applied mathematics. So my model is also has also a motivation from the neuroscience in the sense that current neural networks are not are more and more departing from the true functioning of the biological neurons, and there is value in taking inspiration from this from what we know from how the brain works. So ENCODE is about just taking a hybrid approach between deep ONNET and numerical methods for partial differential equation, and we will show that it actually have nice generalization property temporal generalization property, and it also have the potential to reduce the number of parameters and the sample efficiency and the sample complexity when fitting partial differential equations. So to begin with, I'll go over the Normale model, which I'm sure most of you know. It's a nice hybrid model also that defined depths in and or recurrence in classical deep neural networks as time time in a time marching scheme, in a solver time marching scheme. So what the parameters of your neural nets are learning in this model is the vector field. So the differential equation, the temporal derivative of a particle x, that is, when integrated, yield a flow map from a specific initial value to its final state at t. And if you are trying to do and with that in hand, you can learn a particular flow map to perform representation learning or to fit a physical system. But there is one representational limitation of node. By design, they have limited approximation capabilities in the space of homeomorphisms on a vector space. And there are results that show that you need at least twice the amount of dimension to become a universal approximator of homeomorphism in this space. So to give you, to be more concrete, you have this, for instance, one-dimensional crossing trajectory problem. So let's say that you want to fit the function which at x associate minus x, which you read out at time t equal 1. So the x-axis here is the time. So and the y-axis is the input to your neural audio. There is an indetermination at 0 because the model receives contradictory signal because, of course, it has to transport continuously the particle at 0. Half of the data points will drive the learning towards a vector field that is negative, on the other hand, and conversely for the negative domain. So we came up with two solutions for this problem, which actually lift this model from function regression to operator regression, and I will explore and discuss more how this relates to deep nets. But with those two solutions, one is to learn a flow that is dependent on the initial state. So if you, for instance, for the same function, if you condition the vector field by, for instance, the sign of your initial state, then you are good to learn this function. Because now the negative signs can, but because you are learning a family, actually a family of vector field rather than a single vector field. You can also learn a vector field that is changing with time, that is non-autonomous, and potentially dependent on the current activation of your neural networks. And that yields the second solution to this problem. So that's the general definition of our model, and actually they relate to two types of control in optimal control theory. One is called open loop. So you a priori give some control to your dynamics, so that such that it is conditioned in a particular way, or you change the control signal is changing the action of the function f over time. This is related with notion of synaptic plasticity in neuroscience, and it can yield, as I was saying, a model that is not only doing function regression but operator regression, because it learns from initial state a family of vector field. And so we empirically looked at the solution, and we show that it actually breaks the topological constraint associated with neural ODEs. So for instance, this two-dimensional annulus dataset, you cannot linearly separate your points with a regular neural ODE, and you can obviously do it with the open loop and the closed loop control to a perfect separation. It has also interesting behavior for memorization, and in the case of another experiment, we looked at how the synapses, so the parameters, the fact that they evolve with time, can support fast memorization of bit patterns, and we show that they really changed the sample complexity and the capacity of such model to memorize complex representation. So with respect to regular neural networks. So this was in our initial model, and I think it holds some similarity with DeepOnet, in the sense that we have this duality between one network modulating one network that is fitting a basis of function in a specific vector space, and one other, the controller, so the open loop or the closed loop controller, that is modulating dynamically this model such that it aligns with a specific external signal. So just to sum up the DeepOnet formulation, we are specifically interested in fitting operators that are that emerge from a partial differential equation. So the first equation that you see in this slide, and to do that, you have at your disposal a data set of functions u of x t, so u defined over a spatial and temporal domain. And what you want to learn is the operator which at this specific control signal learns the solution y over the whole spatial and temporal domain as well. DeepOperator Networks works by discretizing the control function space and feeding this discretized this tensor to the branch network such that it output the coefficient that will in turn modulate the computation of the trunk networks. And by doing so, you're able to learn this kind of operators. So this infinite dimensional in this this infinite dimensional space, you are able to select the right operator that fits the data. And so if we look at the two model, there is actually a hybrid model that can come from those two formulations, in which we take rather than discretizing the temporal domain, we use a numerical solver to integrate the solution in time, so that and we learn the vector field that is giving rise to this operator with a DeepOperator. So rather than having discretized the sampling of the control signal, you can pass the control signal as a dynamic variable of your integration scheme, and by doing that, you reduce obviously the number of parameters that you need for the branch network. But there is also another benefit, which is the temporal extrapolation. If you have an autonomous system, if you are trying to learn an autonomous system, then you can the final time at which you integrate your model doesn't matter, and you can go to longer time horizon than what you have trained your model for. And that's important because regular DeepOnet cannot do that. As we are currently looking with Bora and Adar, DeepOnet fails outside of this domain because the set of function that it is learning, so this what the trunk net is learning is simply cannot generalize out of the blue, I would say, if it has not been trained for. It's also as the same way as DeepOnet can be regularized with physics informed terms in the loss. For instance, if we know the explicit equation of the temporal derivative of the system, we can train directly the DeepOperator network to fit this variable, and it can also work with any initial value that you want. So rather than learning a specific DeepOnet for a specific initial value, here you can learn because you are breaking down the problem in this way, you can learn a model that is agnostic to the initial volume. So
Matthew, sorry, can I ask a question?
Mm-hmm.
So what is the input to your trunk net? Is the capital T? So
going back to the DeepOnet, what you have is you have sensors which represent your control function, and Y here is sorry, it will be T. Sorry, there is a mismatch in the notation, of course. Okay. Yes.
So it's capital T. So you can do this for any capital T.
Exactly. Yeah. Sorry about that.
Okay. So could you for this slide? So you replace the forward propagation of the trunk net by a neural ODE, by a e-neural, right?
Yes, that's it in essence. Yeah.
So after the training is complete, when you do inference for any capital T and any control U, you have to solve the ODE again, right?
Yes, of course. Yes, that's a limitation of the system. You need to integrate the system to infer the value at some specific time. Yes.
Yeah, got it. Thank you.
So that's kind of a recurrent scheme here introduced as opposed to the regular DeepOnet, which needs only a feed-forward computation in the graph. So that's one of the drawbacks of the method. Plus the fact that there is also error inherent to the numerical solver, which needs to be controlled. And another limitation is the fact that you need to integrate your solution on the whole spatial domain other than selecting for a specific spatial location or coordinate as you have with DeepOnet. For instance, let's say your control is both dependent on space and time, then you have you can select a combination of those two parameters and infer directly the solution. With DeepOnet, you will have to integrate on the whole X dimension. But as I was saying, there is interest in developing this scheme because it reduces the encoding error that is one of the three source of error from DeepOperator, and you mitigate that by having approximation coming from your numerical solver. It doesn't require, in terms of computation, this model does not require more memory than a feed-forward network, because as with Node, we can train it with the adjoint sensitivity method. So deriving the condition from the Pontryagin maximum principle, we can estimate gradient of any loss defined on our solution through this two differential systems that are integrated backwards in time. And so yeah, so that's it for the presentation of the model. I'm going to present a few experiments that are motivated to look at the specific features and advantages of this formulation of DeepOnet, and also to compare with this model. I'll use examples that are taken from the DeepOnet paper, so for which you are familiar with. So to begin with, the simplest system that we can think is, for instance, this pendulum with damping, where the control signal here, U of t, is just a one-dimensional function that is taken in some function space, for instance, Gaussian random field with a certain correlation length, or a Chebyshev polynomial of a certain order. And what you want to model here is the position of your pendulum in the 2D space, given this function. So the model learns with few training samples. So the sample complexity is actually rather reduced. Here, the data set consists in trajectories, coupled trajectories of the control function U and the solution from 0 to t equal 1. And then after we test those models trained with different dataset size to different time horizon. And we see that actually, even though there is some degradation of the result, the system still managed to retain a good performance. So just disregard those two lines. They are for a different setting. What I want to show is just that you have this temporal generalization property, which is not present in DeepOnet. So in the lower panel, you see that DeepOnet is failing on those are the trajectory of the pendulum, and you can see that they depart from the ground truth after the final time t equal 1 onwards. Looking at the vector field, at the control vector field, we see that the model learns the true vector field for here the x-axis will be the first coordinate, so that will be y1, and the y is the second coordinate, and the arrows are represent the direction or the velocity of the pendulum with respect to those two coordinates in three settings, whether the control is positive and equal to 1, whether it's null, or whether it's is negative and equal -1. And we see that the underlying vector field is changing. It is changed on the wall on this whole rectangle of coordinates y1, y2 with errors that are describing those weird arcs that we are investigating, but the error level lies at 10⁻⁵, 10⁻⁶ for this for the vector fields. So that's encouraging, and also it can because we again we have broken down or we have separated this temporal dimension. There is also robustness with respect to the space of control function that we infer our solution from. And for instance, when we test our model with a Gaussian random field with different correlation length for the radial basis function that are equal to 0, 2, we train that for this setting, and then we test on a harder arguably data set because there is more variations in the control, or conversely for smoother control function there is robustness because what the DeepOperator is fitting is the solution that is local in time and not holistic as in the regular DeepOperator approach. And for Chebyshev polynomials, it's also the case. We also tested this model for other applications, and specifically diffusion reaction equations, where the control function here is defined on both the spatial and temporal domain, and is consisting Gaussian random field with the same correlation length with radial basis function, the same correlation length. So you can see some of the samples here on the right, arbitrary samples, and you can see both the run-through solution that were and the solution found by the model with error again satisfactory. The interesting take here also is that we have relative generalization to different control function here, for instance, with when varying the correlation length. An interesting application of this model also is the fact that we can perform PD constraint optimization with for controls that are both varying in time and space. So let's say that we have we can define this minimization problem when we have a reference solution that we would like to reach, where U is a solution of a trained model, and what if U is parametric, then we can take gradients with respect to this to those parameters defining the control function the same way we are training the model by mediating the gradients of the specific loss through the agent method. So as an example, and this is only qualitative, for instance, for the diffusion problem, defining this solution reference and a control function defined with interpolation of values on an equispaced grid, we are able to optimize the control function such that it approach the desired reference solution. And another experiment for a different equation that we tried is the Burger equation, and this time another application of the system that we wanted to investigate is whether we could also learn a full family of Burger equation where the control parameters are here the coefficients of diffusion, so mu and nu. In this setting, what we showed is that you can train your model the same way, varying by sampling mu and nu in your specified domain. So, for instance, here it's between 0.1 and between 0 and 0.1. And the same way the initial value of your solution is a Gaussian random field with L equals 0.2. And you can see again that the model reached a pretty satisfactory solution with the same temporal generalization property. And what is also interesting is that the vanilla null ordinary differential equation have a higher generalization, both training and generalization error with respect to the parameter nu that we tested, mu and nu. For instance, here, when you are on the third panel, when you are varying your parameter mu, you see that, of course, the above 1, where the model hasn't seen any training sample, the performance is degrading, but it's on average better than just passing those parameters as input input to the model in Node. So the dual formulation of the DeepOperator networks helped in this sense, where the influence of those parameters mu and nu is more distributed because of this architectural duality of the branch and trunk net. So that's it for the experiment. I thank you for the attention. The key take that I would like you to get from this is just that that's I think some preliminary results that show that we can there is interest in using those regular numerical solvers and combine them with the database, the purely data-based approach, such as DeepOnet. And thank you. That's it.
Thank you, Matthew. I have a few questions. So,
Sure.
so number one, so the reference paper you put here, I just searched is the title "Go with the Flow"?
Yes, that's it.
But that paper doesn't have any DeepOnet content.
Yeah, true. It's because this is for the second part of the Go with the Flow paper is actually this formulation that I was talking about in the first part, and then now all those this development hasn't there is no reference at this point for this work. Yeah.
So it's like unpublished work for DeepOperator.
Yes.
And another question is, so I just want to make sure that in this DeepOperator plus neural ODE model, you assume that you don't know the ODE explicitly, right? Could you go to the first example?
That's true. For the 3 experiments that I shown, it's a system identification problem where we don't know the true analytical form of the problem, and that's exactly what the 2 last row in the table are actually physics informed training. So in these cases, in those 2 cases, now we don't learn the
physics.
We don't regress the solution with the numerical solver. We just learn the deep operator directly to express the vector field, and then we integrate the solution at test time. And this yield similar results. Because I think that this is a fairly simple problem where there is no explicit advantage of using the physics-informed formulation.
Yeah. So in the end, suppose you don't know the physics, you don't know the ODE. In the end, after the training is finished, you also learn the dynamic systems.
Yes.
So
yes.
How's that? How good is that? How good is the result of the OD system?
So,
like how good is the model for identifying the physics? That's the question I asked.
So you mean then monitoring the error with respect to for instance, those 2 terms? You mean like doing the reverse?
Yeah, something like that. Yeah. I'm curious.
We haven't investigated at the moment. Yeah.
Yes, it's because the final result, the error or the results, they're looking good. So I'm curious if they actually learn the correct physics out of that.
From this panel, I think we can say that it can. At level that are similar to DeepOnet, because here, for instance, I show the overlap of the two vector field for the 3 control conditions, and they are indistinguishable. The color code show that there are errors which are at the level of 10⁻⁵ or 10⁻⁶, if I recall well.
Great. Thank you.
Sorry, can I ask you a question?
Sure.
This is Tim from Brown, and this is a very interesting talk. Thank you for the talk. And can you go back to the DeepOperator plus Ecole? Yeah. Okay. So can you explain a little bit how what's the structure? So you have a DeepOperator which learns the solution operator for the ODE, right?
Yes. So you can do. It's relating to the question from the previous question. You can either do directly operator regression or vector field regression by just looking at what's inside the integral. So this term between square bracket. That will be if you know the velocity of your function of your solution y, you can train against that. There is another way you can train the model, but if you know the exact analytic formula of the vector field, then you can train against it, and that will be the PIN way. And there is the third way where you just perform the numerical integration, and then fit the parameter of your branch and trunk against the error of the found solution for this numerical scheme. And that's where the adjoint method kicks in. When you have no information about your physical system, then you are you can still retrieve your gradient parameters with respect to this to the ground truth solution in your dataset.
Okay, so
more precise on the model. So what the two branch and trunk networks get is different from the regular DeepOnet. In the regular DeepOnet, you pass your sensors, your tensor of sensors of control function evaluated at a sampling of temporal and spatial domain, and you pass the scalar value or the vector of coordinates at which you want to evaluate the function, the operator, the image of the function, the control function by the operator. And in the ENCODE formula, you are not passing this coordinate, but so which is not y here, but t again. Sorry about the mismatch. You pass the states of the current state of your function. So iteratively, you take the intermediary solution of your flow map at time t called small t, and you pass it back to your function. But every time this trunk function gets modulated by a new by the image of the branch net with respect to new sensors that are sampled at t equal small t.
Okay. So F is the trunk net and B is the branch net.
Yes. Same as here in the regular DeepOnet.
Okay. And then you can use the PMP, the puncture gain maximum principle, to train it.
Yes.
Okay.
There's no it's seamless with regard to traditional node. You have no distinction between branch and net. You can just take the parameter of both of your networks in a single estimation.
But then how do you choose your loss function L?
So the loss function is either final value estimate, so you can regress the same way you do with your DeepOnet for a specific norm error after you solve the problem, or as we said, you can take directly the velocity of the system and train against an analytical expression of that.
So do you mean you choose this curly L and this this little L inside the integration? You choose them to be quadratic, or?
So for the experiment I have shown, you don't have this integral, so you are not regularizing your dynamic in any sense, and you are not regularizing the parameters either. You are only penalizing the final sample, the final state of your system for an L2 norm, for instance.
Okay. Thank you.
Of course.
Do we have any more questions from our speaker? All right, if no one has any more questions, just thank you, Mathieu, for the presentation. And yeah, this is for this week's Crunch Seminar. Everyone has a good weekend. See you next week.
Bye. Thank you.
Bye.
Thank you. Bye.
Bye.
Thank you. Bye.
Bye.